Good afternoon, and thank you all for joining today's webinar, the Analysis for Coastal Operational Resiliency, AnCOR, Wide Area Demonstration. There are several dynamic speakers for today's webinar. Next slide, please. Dr. Shannon Siri, chemical engineer with 25 years of experience at EPA. Dr. Siri is currently with EPA's Office of Emergency Management, working in the CBRN Consequence Management Advisory Division. Dr. Siri is focused on the response and recovery from a chemical, biological, or radiological incident. Dr. Worth Calfee, research microbiologist with EPA's Center for Environmental Solutions and Emergency Response. Dr. Calfee's research focus includes sampling, decontamination, and management of waste from CBRN contamination incidents. Next slide, please. Dr. Paul Lemieux, Senior Research Engineer in EPA's Center for Environmental Solutions and Emergency Response. Since 2002, Dr. Lemieux has been working on management of waste from cleanup after chemical, biological, radiological incidents, foreign animal disease outbreaks, and on decision support tools to aid decision makers during wide area contamination incidents. Mr. Timothy Bowe, geographer with EPA's Center for Environmental Solutions and Emergency Response. His work focuses on response and waste management issues following CBRN incidents. He's also been developing computer-based decision support tools to aid decision makers in responding to wide area contamination incidents. Next slide, please. Dr. Lucas Odiance, research physical scientist with EPA's Center for Environmental Solutions and Emergency Response. He's currently leading research efforts to assess decontamination options for fentanyl contamination building material and approaches for effective decontamination of contaminated PPE. And Dr. Michael Perilla, physical scientist with EPA's Center for Environmental Solutions and Emergency Response. He supports a wide variety of research roles related to fate and transport and wide area sampling for emergency preparedness. Next slide, please. And now I would like to turn it over to our first presenter, Dr. Shannon Siri. Shannon?
Can you hear me okay, Amelia?
Yes, thank you.
Thank you. Welcome to the Analysis for Coastal Operational Resiliency Wide Area Demonstration webinar. Throughout the presentation, we'll use the acronym AnCOR to represent the Analysis for Coastal Operational Resiliency program. Next slide, please. We wanted to take some time up front to recognize our partners in this program. The AnCOR program is funded by an interagency agreement with the Department of Homeland Security. Several offices within the Environmental Protection Agency supported the wide area demonstration, including Region 3, the Office of Land and Emergency Management, and the Office of Research and Development. We also want to recognize our partners, the Centers for Disease Control, for their assistance with analysis of the samples that were collected. The Laboratory Response Network, particularly the labs shown below, for analysis of the many samples that were collected. And Fort AP Hill for use of their urban training area. Next slide, please. For this webinar, we will start with an introduction, followed by how we use science to build a foundation for conducting the wide area demonstration field test, followed by the focus of the presentation, that being the wide area demonstration and how the field test was conducted, followed by what is next for the AnCOR program and how the knowledge and tools will be transitioned to the U.S. Coast Guard. And then we will have a few minutes at the end for questions. Next slide, please. The AnCOR wide area demonstration was focused on exterior urban areas. Imagine a U.S. Coast Guard base or station, or an urban area in a large city that has been contaminated with a biological agent, such as Bacillus anthracis. There are a variety of surfaces, such as concrete, asphalt, vegetation, including grass and trees, and many other surfaces. If a U.S. Coast Guard base or station were impacted, U.S. Coast Guard assets, such as boats and vessels, would also need to be decontaminated for return to service. Next slide, please. As we started the AnCOR program, we needed to build a sound scientific foundation for conducting the wide area demonstration. Questions that need to be answered were, how do we sample from these complex urban surfaces, such as concrete, vegetation, dirt, and asphalt? What options are there for decontaminating these surfaces? What equipment is commercially available that could be utilized in an emergency? What are the waste management considerations for wide area biological incident? How can we manage waste efficiently? What are the operational aspects to respond safely and efficiently? And when can an area or asset be cleared for reoccupancy or reuse? Especially for the U.S. Coast Guard, they rely upon their assets to fulfill their mission on a daily basis. One of their concerns was how quickly can an asset be decontaminated and returned to service. Next slide, please. Under the National Response Framework, Emergency Support Function number 10, EPA and U.S. Coast Guard are the primary agencies for responding to a hazardous material incident. Hazardous materials include chemical, biological, and radiological substances, whether accidentally or intentionally released. This would include characterization of the release, cleanup and remediation of impacted areas, including waste management, and being prepared to respond. Next slide, please. The purpose of the AnCOR program is to develop and demonstrate capabilities and strategic guidelines to prepare the United States for a wide area release of a biological agent such as Bacillus anthracis, with a particular focus on mitigating impacts to U.S. Coast Guard facilities and assets, building a sound scientific foundation utilizing bench and pilot scale research that can be applied at the field scale for a biological agent incident, and then using these bench and pilot scale studies to develop and provide solutions for a biological agent incident before it occurs. Next slide, please. This slide shows the timeline of the AnCOR program. The program began in FY19 with a variety of bench scale projects. In FY20, we conducted the vessel decontamination demo on a U.S. Coast Guard response boat. Several pilot scale studies were commenced in FY21, and then the wide area demonstration, the focus of this webinar, was conducted in FY22. The final year of the program will focus on developing guidance documents and tools that will be transitioned to the U.S. Coast Guard that can be used to respond and recover from a biological agent incident that impacts their assets. In preparation for the wide area demonstration, the AnCOR program and tasks were focused on 6 major areas: sampling and analysis, data management, fate and transport, decontamination, waste management, and demonstrations and field scale projects. These all fed into the wide area demonstration that you will hear about shortly. Next slide, please. Each of the bench scale projects could easily be their own webinars, and the products are available at the website that will be shown at the end of this presentation. The bench scale projects were focused on characterizing and improving sample collection analysis methods, particularly for vegetation, building and refining predictive fate and transport models, which we'll touch on in a few slides, developing long-term air monitoring approaches, evaluating and enhancing decontamination methods for a variety of surfaces. Here again, vegetation and outdoor surfaces were the focus of the program. Enhance on-site waste treatment and management. Can the waste be treated prior to transportation for disposal? Was a question we wanted to answer. And developing data management tools. Can we utilize existing technology to help manage the many data streams and help speed up a response? Next slide, please. The U.S. Coast Guard made clear that they need a rapid return to service of their mobile assets following a biological agent incident. One of the pilot scale projects focused on decontamination of a response boat small, or RBS-1. We tested sampling procedures on all the different material types of this boat and then performed 3 different rounds of decontamination. The first round of decontamination was focused on using fumigation with methyl bromide. The second round, fumigation with low concentration hydrogen peroxide. And then the third and final round was fogging with peroxyacetic acid. We not only utilize commercial approaches such as fumigation with methyl bromide, but simple approaches that the U.S. Coast Guard strike teams could implement themselves in an emergency response. One of the major concerns with decontamination is material impacts on the vessels themselves. The onboard electrical system, including engines and electronic packages, were tested following treatment with the decontaminants to verify that there were not any adverse impacts from any of the treatment approaches. Next slide, please. In preparation for the wide area demonstration, we wanted to know what equipment is commercially available and used on an everyday basis that can be utilized in a wide area biological agent incident to help reduce the time and resources to recover from a biological agent incident. There is a variety of equipment that could potentially be used to apply a liquid sporicide in an outdoor setting, such as agricultural sprayers or road maintenance machinery. The question is, could this equipment be repurposed for environmental remediation in an emergency? Next slide, please. The next field scale test was performed from June 2021 through April 2022 at U.S. Coast Guard Base Elizabeth City. During this study, Equipment was deployed to collect precipitation data and soil and water infiltration data. 3 different surfaces, grass, asphalt, and concrete, were sprayed with Bacillus globigi spores, which is a surrogate for Bacillus anthracis, and stormwater runoff samples were collected and analyzed for spore concentrations over time. Base Elizabeth City also provided EPA researchers with infrastructure data such as pipe sites and locations that was used to build a 2D stormwater model that can be run in EPA Stormwater Management Model, or SWIM. EPA researchers then used the spore concentration data collected during the field campaign to calibrate the model. A hypothetical scenario of a plume of spore contamination across the base was then simulated, and the stormwater model was used to predict spore transport over different sized rain events. I will now transition to Worth Calfee to start the wide area demonstration description.
Thanks, Dr. Siri. Is my audio okay?
Good copy.
Next slide, and then one more. All right, so Shannon provided the context of why EPA and US Coast Guard and DHS are involved in bioincident remediation, and how under the AnCOR program, we've progressed from bench scale to pilot scale to develop response capabilities. It's my pleasure to introduce the AnCOR Wide Area Demonstration, or the WAD, which is the main topic of this webinar. It's where we take the developed capabilities from the bench and the pilot and put them together in a field scale assessment. We learn a lot through bench and pilot scale research, such as what conditions are effective for decon, how and where to collect samples, and the best methods to analyze them. But we need to understand how effective those methods are against a realistic challenge and how difficult or time-consuming they are within the overall response. The WAD allows us to put all those pieces together to see how they work as a system. And this includes sampling, data management, waste management, sample analysis, entry, movement, and exit of operators in the PPE that they will be required to wear in a real anthracis incident. And this systems assessment is critical for understanding how well our developed capabilities perform and at a realistic scale. It allows us to identify pinch points, effort and cost that's required for these operations, and understand where our capabilities work and where they don't work. And then we can rethink those components that don't work and optimize those to better improve the response. Next slide. So when we started planning our test, we needed to identify a venue. So we started thinking about the requirements that would be needed. First of all, we wanted a realistic scale. We didn't want to do bench scale work outdoors. So we wanted a place to stretch our legs, to challenge us. So something large-ish, large enough to use full-scale equipment, full-scale response tactics and methods and strategies. We also wanted representative features of a US Coast Guard base, but that also means representative of an urban area. So streets, sidewalks, grassy areas, trees, shrubs, buildings, those things that challenge the decon. And one of the important points, we wanted to be able to release our surrogate organism into the environment. And Fort AP Hills Urban Training Center, the Asymmetric Warfare Training Center, met all those boxes. You can see it pictured in the top left image. The yellow square is the test site. That's a 2.2 acre test site that contained all those aspects that we were desiring. A 5-story building that you see in the top right building, but also grass, trees, sidewalks, streets, those things that would challenge our decon operations. Next slide. So here you see the sequence of events, or the test calendar. And I want to stress, this is only the 4 weeks or the 1 month of active testing. It doesn't show the months and years that went into planning it before this event occurred. So in the first week, this was May 2022, we had delivery of our equipment, site setup. We did background sampling. On the second week, our samplers arrived and we trained them. We also inoculated the test site, did our deposition, and did pre-decon sampling. So the characterization sampling following inoculation. In the third week, we conducted our decon operations over 3 days. We did post-decon sampling after that and waste treatment operations. Then in the fourth week, we did our waste sampling post-decon. We cleaned up the site and organized and demobilized. Next slide. So whenever we conduct these field scale tests, we like to do them as real as possible or as similar to a real incident site as possible. We set up support zones, contaminant reduction zones with decon lines, warm zone, the decon line, and the hot zone. So it's important to get a realistic assessment of how our capabilities work together if we're doing it as closely as possible to a real incident, following the real procedures that would be done in a real incident, wearing the PPE, going through decon line. So all this is done to get us a more accurate picture of how our pieces work together. And by the way, we're tracking cost and time and effort for each of these tactics. So we understand how long it takes and where the pinch points are. And it helps us operationalize and make things more efficient on the back end. Next slide. So just briefly wanted to introduce the inoculation procedures. I think this will help set the stage for the sections that'll come later. We used BG. It's a surrogate for Bacillus anthracis. It's Bacillus glabigii. It's in the same genus as Bacillus anthracis. We contaminated only a portion of the site, as you can see on the map on the right of the screen. We contaminated a representative amount of each kind of surface type, basically. And we used the speed of the toe. That's me, by the way, pushing the toe in that middle image, and Dr. Siri supervising or co-piloting, whatever you want to call it. So we used the speed of that toe as well as the titer and the flow rate of the commercial off-the-shelf lawn sprayer to achieve a 1 × 10⁷ spores or colony-forming units per square foot target. And we also used a backpack sprayer to go up the building and contaminate areas at height so that we would have a challenge for the sampling and decon operations that would follow. Next slide. So it's my pleasure to introduce Dr. Michael Perala, who's going to talk about sampling and analysis methods.
All right, thank you, Dr. Calfley. Can everybody hear me okay?
I got you loud and clear.
Awesome. All right, so Aaron Silvestri and I were the test bed co-leads for the sampling and analysis portion of the AnCOR wide area demonstration. The photo that you see on this slide shows some of the members of our sampling group. We had a pretty great team, which was very helpful since the logistics for obtaining all these samples was a pretty large undertaking. Next slide, please. So jumping right in, the first main objective of the sampling portion of the wide area demo was to demonstrate the use of traditional biological sampling methods, but to scale those traditional methods up to a full-scale outdoor setting. Additionally, since this was a research project, it was a good opportunity to demonstrate newly developed or somewhat more non-traditional sampling methods in that full outdoor setting, as opposed to them just being applied to the lab bench scale that was mentioned a little bit earlier. So our goal for this project was to perform 3 rounds of sampling. First, we gathered background samples to see if there were any detectable levels of bacillus spores present on a wide variety of surfaces before contamination. And once the controlled inoculation occurred, we then performed our first full sampling campaign to characterize the magnitude of spore contamination. Once the decontamination agents were applied to the sample test area, we then completed our whole sampling methods again to see if the decon agents reduce the spores compared to the pre-decon levels. Next slide, please. So on the left side of the slide here, you can see some examples of our traditional sampling methods. Those are some of the methods that have been used or they're tried and true in the field. Those include sponge sticks, which is essentially a sponge attached to a plastic stick and is swabbed on surfaces within a sampling template. We also gathered surface samples using 37mm filter cassettes, which I'll be calling microvacs for the remainder of this presentation. It's basically a mini vacuum that pulls an air sample through a hose, and any spores that are drawn through that vacuum get deposited on a small filter. The microvacs were also sampled on a template as well. Prior to decon, we also laid out an array of reference material coupons, or RMCs, through the test area to get a general sense of the spore recoveries. The RMCs are basically just 1 by 2 inch metal coupons, and they're laid on flat surfaces for the inoculum to be deposited on. And finally, we set up an array of dry filter unit samplers, or DFUs, around the perimeter of the test area to measure if there was any spore transport that was occurring outside of the main test region. These units draw an air sample through the top of the box, and any spores would be deposited on a felt filter. So on the right side of the slide here, you can see some examples of our newer or non-traditional sampling methods that we examined during this field project. These included grab samples where bulk materials were gathered by hand off the ground surface and dropped into a Nalgene bottle. We collected leaves directly from living trees and shrubs, gravel off the ground surfaces, ground litter, which consisted of things like dead leaves and pine needles, and other samples like grass. For the grass samples, our samplers used handheld cutting shears such as that one you can see in the bottom middle part of this slide. Additionally, folks on the test bed also collected some waste samples from maritime-like material such as ropes and life jackets. And finally, a new sampling method that was recently developed in our group called the Activity-Based Aggressive Air-Contained Sampling System, or ACCESS, was also demonstrated, which essentially stirred up spores on the surface and drew any airborne spores through a filter, which is almost like a huge vacuum cleaner. Next slide, please. So to facilitate easier and sterile sampling, kits for each sample were pre-assembled at EPA in Research Triangle Park, North Carolina, and shipped in boxes organized by sample type. Each kit was containing the sampling element, and any necessary supplies were enclosed in an overpack bag and pre-labeled with a QR code for sample documentation. So on the top of this slide, you can see examples of the kits for each of the different sampling types that we collected. The kits and any other supplies, such as bleach, wipes, and gloves, were also packed on site at the field study into clean sampling backpacks, such as those that you can see on the bottom middle part of the slide. And the backpacks were packed for each entry team, depending on which samples that team was assigned to collect. Next slide, please. So to ensure that the samples were collected properly and aseptically, we provided training to all of our sampling team members, which helped us to evaluate decontamination technology performance and to ensure data quality objectives. So a few weeks before the field study, our sampling group provided virtual trainings via Microsoft Teams to any of the samplers to demonstrate the sampling steps and how each sample should be collected for each sample type. Additionally, the sampling teams received on-site training before each round of sampling. And then the teams were also provided a laminated handout of each sampling procedure so that they could reference it on the spot in case they forgot any steps. Next slide, please. So each sampling team consisted of 3 people, which was the collector, the supplier, and the data manager. The samplers were able to choose their roles, but they were asked not to change their role in order to maintain sample integrity and prevent cross-contamination. So the collector physically collected all of the samples and carried the analysis backpack, which contained the completed samples. The collector did not touch any of the clean supplies and sampling kits. The supplier, on the other hand, provided the collector with the sampling materials from the clean backpack. Supplier did not come into contact with any of the samples or the relevant materials. And the third member of the sampling group was the data manager, which carried the clean backpack, and it contained all of the sampling kits. And this person also directed the team to each of the designated samples using a tablet and a GPS device. That person was also responsible to document each sample and provide radio communication while the team was in the hot zone. Next slide, please. So as I mentioned a little bit earlier, we provided on-site training to the samplers, and they were able to perform a dry run of each of the sampling procedures. We pre-assigned teams of 3 and issued training backpacks so that the teams could try to collect each sample and ask any questions to clarify sampling techniques before they actually entered the hot zone with their full PPE. We set up training stations for each sample type, and between the 2 main rounds of pre and post-decon sampling, we trained roughly about 20 to 30 EPA folks and about 9 US Coast Guard people per round. Next slide, please. So I'm not going to go into great detail here since Tim will next go into discuss the data acquisition component of the wide area demo. But I just wanted to mention that during the on-site training, samplers were also able to perform dry runs of navigating to each sample point, and the data managers were able to operate this iPad mini tablet device with a GIS app. Each sample was displayed on the map, and the team navigated to each sample using a real-time sub-meter GPS device, as you see in the photos here. Next slide, please. So during the background sampling, we collected 35 field samples across the study area, which was a subset of the main group of samples. The background sampling also consisted of 6 field blanks, which were samples that entered the hot zone, but were not essentially touching any surface or not collecting any physical sample. Additionally, 9 media blanks were sent to the lab as part of the background sampling, but those did not enter the hot zone. We then collected 200 field samples during each of the pre and post decon sampling phases. Those samples were paired in space to understand decon efficiency, and a subset of those field samples were collected outside of the area of contamination to understand if spores were being transported outside of the contaminated zone. So in the figure on the right, you can see our test area and all the different test square areas and the locations of each sample. The purple and the yellow dots show the microvacuum and sponge stick sample, which mainly occurred on and around the building towards the left side of the sample area, mainly on the asphalt and concrete surfaces. In the middle of the test area, you can see green and blue dots, which were mainly grass and gravel grab samples. And then on the right side of the field area, near the tree line, we collected leaves, ground litter, and some further grass samples. So these, during each of the pre and post decon sampling, 20 field and 11 media blanks were also taken. And all these values are exclusive of the reference material coupons, the waste samples, DFUs, and excess samples. Next slide, please. This slide shows the different surface matrices that we collected for the samples. So for example, I just wanted to highlight that mainly the micro vacuum cassettes, sponge sticks, access samples, and RMCs were taken from asphalt and concrete surfaces. Out of all the vegetative surfaces, those were mostly grab samples, including RMCs, except for the grass, where we also experimented with a few sponge stick samples. So in total, across the entire field study, 879 samples were collected, which also includes all of the blanks. Next slide. So a little earlier, I also mentioned we took air samples using dry filter units, or DFUs, to measure if any spores were dispersed through the air. So each day of on-site activity at the test site, these units ran for the entirety of the workday, and you can see the map on the right that shows 10 DFUs in yellow that were positioned around the perimeter of the study area. So over the 10 days of on-site activity, we collected 100 DFU samples. And then during the day of our waste sample collection, we installed 3 additional DFUs around that sampling area, which you could see on the blue dots. That also included, there also was additionally 20 field and 13 media blanks collected for DFUs. Next slide, please. So once all the samples were collected, after all the samplers entered the hot zone and came back out with all the samples, they were moved to a sample processing trailer and stored in on-site refrigerator until shipment to the labs. All of the grab samples, however, needed to be processed on-site before being shipped to the designated labs. So in that processing trailer within a fume hood, each sample was weighed, and then a pre-measured amount of PBST surfactant was added to the sample. The sample Nalgene bottle was shaken for 2 minutes in the fume hood, and the liquid solution was then decanted into the PBST container, and only the decanted liquid was shipped to the labs. All the other samples were sent as is to the labs. Next slide, please. So when it was time for the sample shipment, the samples were removed from the on-site refrigerators and packed into coolers with all the samples that were assigned for each designated laboratory. During this time, a chain of custody tool was used to scan a QR code for each sample, to create that chain of custody form for shipment. Those coolers were then sent via FedEx overnight between the days of Monday and Thursday, so that each lab could receive their shipment on a working day, so it didn't have to sit in receiving over the weekend. Next slide, please. We wanted to acknowledge all of our partner labs that provided analysis for the AnCOR samples. A majority of the samples were sent to EPA's Research Triangle Park BioLab for analysis. However, many sponge, microvac, and grab samples were also sent to CDC and LRN labs. We did this to foster collaboration among EPA and CDC and LRN labs, and to practice what would need to occur between multiple labs if a real biological episode were to happen. Next slide, please. So once the labs received the samples, they were cultured onto spread plates and microfunnel filter plates. The number of colonies that were indicative of bacillus spores were counted on each plate, and the results were provided in the number of colony forming units, or CFUs. So as part of established methods, the detectable range for spread plates was between 30 and 300 CFUs and 15 to 150 CFUs for filter plates. So because this method of counting was not always straightforward, we had to establish some data quality control tiers to determine which plate counts would be useful for further sample calculations. Next slide, please. So sample data was divided into 4 main categories. Samples that were detect contained a number of CFUs that were within the detectable range. Adjusted detect occurred when spores were noted on the plates, but were just below the limit of quantitation, or LOQ. So those results were adjusted to the LOQ. Samples that were indeterminate occurred when there was excess background contamination on the culture plates. So the results of those samples were adjusted to the limit of detection, or 1 spore per plate. And finally, a non-detect sample was when no CFUs were present. All right, so that wraps up my part of the slides here. And with that, I will pass the presentation off to Tim Bowe for data management on the next slide.
All right, thanks, Mike. Just doing a quick mic check to make sure folks can hear me.
Heard.
All right, maybe nervous there. All right, so I'm going to include or just give a shout out to a few folks who were part of the data management group, or the A team. That's Jordan Deegan and Matt Blaser from EPA Region 5. Next slide, please. Yeah, so regarding data management, let's talk about a few definitions. What is data? Well, data is pretty simple, right? We deal with data and use data on a daily basis. For the purposes of this presentation, we're going to focus in on just information that's collected either for analysis, reference, or data keeping or archiving. Data management, on the other hand, is the practice of collecting, storing, and using data to support decision making. However, it's an ever-evolving discipline. So as a data manager for a disaster or emergency response, and the same is true for this field study, is that it included a lot of other things, such as GIS, development, software development, supporting the sampling team that Mike just touched on in terms of visualizing data. So there's a lot going on here. So data management isn't just about saving a file to a computer. It's a lot more than that. It's about looking for innovative ways to collect data, to store it and visualize it. So again, those decision makers can make decisions and move forward. I want to point out it's a really cool quote down here. Data management is not only about handling the raw ingredients, but also about artfully crafting them into a rich and informative feast for decision makers. I'm on the West Coast, so it's almost lunchtime. So I'm going to use another sort of analogy here is they always say never go to the grocery store hungry, but always go to disaster data hungry. It's really easy to collect a lot of data, but it's not easy to replicate the study in case you didn't collect data that you needed, right? So you can always get more space to store the data, but you can't always go back out there and collect the data that you need. So I want to hit home on that. Next slide, please. So let's talk about the process. So disasters are like thumbprints. Everybody's unique. You may have been a disaster or emergency response lead or a manager for a disaster response, and your approach might look different here. But I just wanted to kind of go over what we did. And my presentation is going to follow this process as best we can. As Dr. Siri mentioned, that each one of these topics could literally be an hour presentation just on its own. We're going to go into things such as site recon. We're going to talk about how we design the sampling plan. We're going to talk about data acquisition software, the network that we use to collect those data while folks were in the field, how we monitored that, and then how we got the information back from the lab and visualized the results. Again, just highlighting the three important phases of preparing for this, deploying assets, and then validating the data when they came back from the laboratory. Next slide, please. So I mentioned recon. We deployed some pretty cool technologies as part of our recon process. And so just to touch on what recon is it's understanding the environment that you're going to be working in, right? If you're going into a situation blind or not knowing a lot about the environment that you're going to be working in, it's hard to make decisions, and it certainly makes planning a lot more difficult. So on the far left, we have the 5-story building that Worth mentioned. In the middle is that building imaged using a LiDAR or 3D scanner system. We were able to take that and then create a simple polygon model that can be used for to support our sample plan designs, but also for navigation. So this 3D imagery was loaded on those iPads, so folks could use that to sort of orientate themselves in the environment and also navigate and determine where the samples needed to be taken. Next slide, please. So the sample design process, as Mike just covered, we had to collect a lot of samples. And to design that, we were looking at a targeted sampling design. Now, again, as Worth mentioned, that this was a study, but we also tried to replicate this study as close as possible to a real-world event. So for this incident, we actually used the trade-off tool for sampling to develop our targeted design. The importance of the trade-off tool for sampling, or TOTS, is that it's a GIS-based tool. It does two important things. One, it gives us a cost estimate and time estimate based on the plan that we develop, but it also enables you to develop your plan in a GIS. What's important about that is that each one of these sampling locations we had to navigate to once implemented. So if you keep it in GIS, your life is certainly easier when trying to segue this effort into operations. In the middle there, you can kind of see an image of how we were plotting samples on the surfaces, on vertical surfaces, acknowledging that the world is not 2D, it's 3D. So it's helpful if you understand both the horizontal and vertical planes of where samples are being attached to. And on the far right, you see a snapshot of the form, which we'll talk a lot more about here shortly. And also a sampler there who's holding a GPS pole with a sub-meter GPS and their iPad connected to it. They use these technologies in combination to document and locate samples. Next slide, please. So data acquisition form, we use field maps, except it was more or less a customized version of field maps. The field maps form allowed teams to sort of sequence samples. So in other words, they would start off with sample 1, 2, 3, and 4. We did this to help navigate teams around an area. So if we wanted them to avoid a clean or potentially contaminated area, this sequencing helped that navigation. Navigation was aided by the use of the sub-meter GPS unit, so teams knew where samples were located, how close they were, and what direction they needed to head in. The data entry forms were fairly simplified in terms of when they would get a sample, they would scan a QR code, and it would fill all the information out onto the form for them. That was done to reduce error and, again, make it a lot easier for folks to enter data in the field. We also built in error checking on the back of the form, so if folks made a mistake, it would let them know before submitting the data. And of course, everything was submitted to the cloud, so we could see these results in real time. Next slide, please. So I wanted to kind of give an overview, again, emphasizing that every disaster response is different. Can you hit slide forward maybe 2 times here, just so we can fade into the slide? There you go, maybe 1 more time. And you should have technologies appear next to the cubes 1 more time. And so what this slide is going to show is how the network was devised. We were working over about a 3-acre area, and we were actually using the building as sort of an antenna. We're using a plumb box, which is the top right, which was our source for internet. That plumb box was connected through a switch, which is located inside the building. And on different sides of the buildings, we also had Wi-Fi repeaters. This enabled us to saturate the entire area, both the building and the field in which we were working in, with internet, again, emphasizing the need to have access to the data as they were collected so we can monitor things in real time, so we can correct mistakes in real time as well. Next slide, please. So this is how that GPS iPad data collection system is sort of built. Again, on the top left here, you had the sub-meter GPS on top of the survey pole. We had it wrapped in plastic to make it easier to decon. We had the iPad that was connected to the GPS pole. And again, they would sort of detach that iPad if they needed to scan bags or take pictures of things. So that was a fairly nice system that they could just carry around with them and record data. We had a pretty cool system set up where as folks were donning PPE, they would travel past the data management station. The data managers would have the device and the samples for each team pulled up and ready to go. The data management lead would grab the device. We would double check with them that everything was okay, and then they would enter the hot zone. They would collect their samples, document things, go back to the decon line. As you can see, the bottom right hand, they would drop the, well, hopefully not drop, but place the GPS system into a, I think that was a trash bin that allowed us to collect things. So the sample teams would go to the decon line, and once the decon line had cleared them, they would go back and grab the equipment and decon it. Next slide, please. Yeah, so this slide just shows an example of that sampling dashboard. This saved us a number of times, again, emphasizing the fact that you're able to make corrections if a team forgets to take a sample or potentially collects the wrong sample. You can correct it while the team is in the hot zone. And we had it where before teams even exited the hot zone, they would radio into the data manager to confirm that they collected everything. That enables you to correct a problem. So if the team needs to go take another sample, it's easier to do versus the team going through the decon line and then realizing you missed a sample and having to send a whole new team out. So our dashboard here shows where the samples were taken. They would toggle on and off if they've been collected, and also keeping track of the number of samples in real time and metadata behind those samples. Next slide, please. I mentioned earlier that it's always good to collect more data than not enough data. And one cool thing that we did is we actually had a GPS system attached to some of the trucks that we were using to apply decon that Dr. Calfee will talk about here shortly. We came up with a cool way to make sense of those various different points that the system was collecting so that we could determine where decon application had been applied, but also where multiple applications have been applied. So if you look at the right-hand side, where you have like sort of a light purple color, that tells us that there were a large number of applications in this area versus the lighter or teal color means that roughly about one application had taken place there. Again, so emphasizing that we were able to use this information to make sense of data. We decided at last minute to attach a GPS system to a truck so that we could monitor that, and then we're able to actually use it later on for some pretty cool analysis work. Next slide, please. Yeah, so this is my last slide. So just want to call out that everything we've talked about here, we've either developed or improved. And this was one of the things that we as a team developed in terms of developing or generating chain of custody forms. When the samples would come out of the hot zone, they could either be scanned or generated per team. So by doing this, the chain of custody tool automatically generates an EDD and a COC, or chain of custody form, that could quickly be passed off to the lab. If you've ever had to do this in the field, this takes some time. We developed this technology so that it made that process a lot easier. So once the samples went to the lab, that came back, there's also the process, which we don't show here, of validating that sample, which is very important to do. And then taking that validated information, as Mike spoke to, and creating maps. So again, speaking to the visualization of the information to make sense of it, which was obviously an important process of this study. And hopefully we'll be able to show some of those slides either as part of our report, or some of those maps as part of our report or part of this presentation. So I think at this point, I'm going to move on to the next slide and hand it off to Dr. Calfee.
All right. Can you hear me okay, Tim?
I can hear you loud and clear, Worth.
All right. Thanks. Next slide. So our objective for the decon was to take what we had learned from the bench and pilot scale tests and apply in a realistic setting and on a scale relevant to the real world to obtain a rigorous assessment of our current capabilities. More specifically, we wanted to evaluate the efficacy of our decon procedures for outdoor settings, and we wanted to evaluate the efficiency and ease of operations so we could learn and improve. Next slide. So results from our bench scale test showed that HTH, or high test hypochlorite, was effective on built materials such as concrete and asphalt and steel. And PAA, or peroxyacetic acid, showed good efficacy for vegetative materials such as grass and shrubs and trees, things you saw in our test area. From the lab test, we found that an application rate of 16 gallons per 1,000 square feet was effective for both decontaminants and all materials tested at the bench. But when we take those to the field, it's much more difficult to precisely achieve a target dose due to the complexity of outdoor environments, the scale of equipment. There's added challenges of conducting operations outdoors, unknown environments, wind, weather. So we added some operational insurance and doubled the application rate. It's better to get it right the first time when you're doing a response. So we doubled the rate to 32 gallons per 1,000 square feet. That was our target application rate for both decontaminants. Next slide. So a little bit more about the decontaminants we used. HTH, again, high-test hypochlorite, also known as calcium hypochlorite. We use that at a 25,000 ppm, which is about 30 pounds per 100 gallons. Now that's about 5 to 10,000 times more concentrated than you would use this product as a pool shock. And it is a commercially available product. It's used for pools, to chlorinate pools. So it's readily available. It comes as a dry granular powder. So it's easy to ship to site and it has a long shelf life, which lends itself to operational ease. We did see a little bit of solubility issues when using it in the field. Solubility was not instant, but we were easily able to overcome that in the field. Peroxyacetic acid, again, that was our decontaminant used for the vegetated surfaces, so trees, shrubs, grass. You can purchase PAA as a concentrated liquid. We used jet oxide, which is a commercially available agricultural pesticide. It contains 15% peroxyacetic acid. We used it at a 0.5% final concentration, so a 30-to-1 dilution. And PAA was much easier to prepare batches in the field, as it didn't require time to solubilize like HTH. Next slide. So when we started planning the decon process, we mapped out where each decontaminant would be applied and determined how much surface area was within each of those decon units. In the map on the right, you can see 3 main decon units: the gravel area, the vegetated area, and streets and sidewalks. So the gravel area and the streets and sidewalks were both areas for HTH application, and then the vegetated areas where we applied PAA. You can also see in that map the building as a 4th decon unit. And then on the left, you see a table with those broken out with total surface areas. We further broke down the vegetated area into 2 separate sub-decon units, grass and a tree and shrub area, because those require 2 different application methods. But overall, you see that our site was 120,000 square feet. So at 32 gallons per 1,000 square feet, that our target application total volume was 3,840 gallons of decontaminant. Next slide. So how did we, and there's a video, okay, thanks. How do we apply the decon to those various decon units? Remember, one of our objectives was to utilize decon operations and equipment that would be representative of a real world incident. In previous large-scale incidents like Fukushima, repurposing commercial and municipal equipment for emergency response remediation was highly advantageous. So for the horizontal surfaces, we selected commercially available, commercial off-the-shelf COTS boom type sprayers, common in agricultural settings. They come in many sizes and shapes. We used a 12-foot boom sprayer that had 7 nozzles. It effectively gave us a 14-foot wide spray width. We had a 500-gallon tank, chemical resistant pump, a 5.5 horsepower motor. We were able to achieve about 8.3 gallons per minute application with this one sprayer. And this sprayer was appropriately sized for our 2.2 acre site. For an actual incident, you would either have more and or larger sprayers in your operation. Next slide. All right, for the vertical surfaces, we selected a commercial off-the-shelf agricultural tree sprayer. This sprayer had a 5.5 horsepower gas motor, a chemical resistant pump, a 300-gallon tank, and a spray gun that could reach about 400 feet vertically and 9 gallons per minute flow rate at 200 PSI. Now, if you remember, we had a 5-story building that was approximately 60 feet tall. So to make up that extra 20 or 25 feet of distance, we used a boom lift. In a real incident, for real tall buildings, maybe spraying from the top down or running decon down the side of buildings may be an option, depending on how high you need to go. Next slide. So just to summarize our decon operations, we applied 685 pounds of high test hypochlorite or 2,250 gallons of the 25,000 ppm HTH liquid. We applied 60 gallons of the 15% PAA or 1,800 gallons of the diluted 0.5% PAA. In total, we applied 4,050 gallons over the 120,000 square foot study area. And if we do the bookkeeping, looking at the actual volumes applied, we were happy to see that we achieved about 34 gallons per 1,000 square feet. We're a little higher than the 3,800 targeted, but that's okay. We were right on with 34 gallons, 32 gallons, sorry, per 1,000 square feet. Then we conducted decon operations for a total of 12 hours and 61 total person hours. And it was interesting when we broke that down by decon unit, regardless of whether we were spraying buildings or the tree area or the boom spray operations, they all were on average about a half a person hour per 1,000 square feet. Next slides. And I think that's it for me. Yeah, I'm going to hand it over to Paul Lemieux to talk about waste.
Thanks, Worth. Can everybody hear me?
I got you loud and clear.
All right. Next slide. Okay, well, one of the things that talking with our responders, one of the things that has kind of come clear is that there's certain parts of the waste management process that are more easy than others. And the Ebola outbreak in 2014 really highlighted that the transportation and the treatment and disposal was one of the more difficult parts of it. Next slide. The estimates that we have from a wide area anthrax incident are that we could be generating potentially tens of millions of tons of solid waste and hundreds of millions of gallons of aqueous waste. So it's not a trivial amount. In order to transport the materials to a disposal facility or a treatment facility offsite, we would have to use the DOT Category A infectious agent packaging, which ends up putting everything into like an 85-gallon overpack, triple overpack. And it's very stringent, and what it does is eliminates most of the potential treatment facilities because these things won't fit through the door. So the idea is if we can figure out how to treat the waste on site and designate it as conventional solid waste, it could be transported to the treatment and disposal facilities using the same protocols as our municipal solid waste. Next slide. So we worked with the North Carolina State University's Nonwovens Institute to develop a semi-permeable material to make waste bags out of. The idea being that fumigants can get in and spores can't get out. So it had about a 2 or 3 micron pore size in the material. We tested it at bench scale to verify the effectiveness of the concept, and then we made a bunch of 35-gallon bags from the proposed material. At the wide area demo, we got a bunch of materials that the Coast Guard had set aside for us, including ropes, swim fins, life jackets, and we added materials like vinyl boat seats and carpet and wood. And we inoculated it with the same surrogate spores that everything else got inoculated with. We loaded the bags and put them into a 20 cubic yard roll-off container. And then we had a fumigation contractor came. It was the same company that did the Hart Senate office building back in the Amerithrax incident. And they fumigated the tinted roll-off in using chlorine dioxide. We then, after we vented the roll-off, we did sampling of the materials in the bags to identify how well we did on the deactivation of the spores. And it's all going to get written up into a concept of operations that our responders could use. Next. So before we went out into the field for the wide area demo, we did this set of tests at bench scale to verify that we could get the fumigant and the moisture needed to achieve the appropriate fumigation conditions. We did it in a glove box inside these small metal containers that had the material covering one end. So we put a bunch of coupons that had known quantities of Bacillus atrophaeus in them and introduced chlorine dioxide and moisture into the glove box and then analyzed them afterwards. We were trying to target the same fumigation conditions that were found to be successful in previous responses, namely 9,000 ppm hours of chlorine dioxide at a minimum of 70% relative humidity. Next slide. Here's an example of the trace of the chlorine dioxide inside the container and inside the glove box. And you can see it only took a few minutes for the concentration of the chlorine dioxide to permeate through the material and have the same concentration inside the little containers as is in the glove box. Next slide. We also had to do the tests to determine whether the spores didn't get out of through the material. So we nebulized some spores that went through the non-woven material as well as through a cellulose acetate filter that would theoretically block them all. And we were not able to see a statistical difference between the filter and the non-woven material as far as being impermeable to the spores. Next slide. So we placed the waste bags into a 20-yard roll-off. We encapsulated it using a polyethylene, high-density polyethylene tarp. It was then fumigated using chlorine dioxide, and then we collected samples. Inside the roll-off, we put gas sample lines in 2 of the bags, and we put 1 gas sample line in the freeboard of the roll-off so we could monitor the chlorine dioxide and moisture content inside the bags and inside the roll-off, as well as the temperature. They did titration in order to measure chlorine dioxide since we didn't have a continuous monitor. Next slide. Here's a couple photos. You can see the chlorine dioxide generation equipment, placing the air sample or the sample lines into the bags. And you can see we used a forklift to pick up the roll-off and wrap it in the tarp in order to tent it so that the chlorine dioxide didn't get out, because it's pretty toxic. We had to monitor that in the air surrounding the tenting as well to make sure that nobody was being exposed to it. Next slide. Here's an example of the results from the titration of the chlorine dioxide. The green line is the concentration that's measured at different points in time, and the orange line is the integration of the green line. So it's the area under the curve. So we were trying to get to a minimum of 9,000 as our conditions. Next slide. So then we opened the bags up. We wore a level C PPE with a chlorine vapor cartridge on there, just in case there was some residual chlorine dioxide in the bags, and there wasn't, based on the monitors that we did have. We collected the samples, and we had also put some biological indicator strips into the bags and collected them as well. Next slide. The results from the waste, we found that all of the materials, with the exception of the wood and the carpet, which have been bad actors in the past, as almost no matter what decon approach you use, carpet and wood are particularly pernicious for resisting the decon. So we did get 1 hit on the carpet and 1 hit on the wood, but 0 hits on all of the rest of them. We tried some sampling approaches to simplify the sampling for any of the responders, because one of the goals of the waste management part of the wide area demo is to try to minimize potential worker exposure that might happen if this were a real incident. So we included that as part of our approach. Next slide. So we've successfully demonstrated this concept at bench scale. We've successfully demonstrated it in the field. We have a journal article in the works for the bench scale tests. It appears to be a feasible approach. The carpet and the wood are, maybe you have to run them through the fumigation twice in order to kill all the organisms on it, but it's not really surprising that those materials gave us trouble. The material worked very well at keeping the spores out and letting the fumigant in. If we were to do this in the future, we'd need to partner with some sort of bag manufacturer in order to make the bags out of the material, because the way they were kind of put together using an ad hoc approach due to time limitations made it so that the side seams of the bags, it was easy to put some of the pieces of sharp material through it. So we use Gorilla Tape to reinforce the seams, but in a real situation, you'd want to have them manufactured by a real bag manufacturer instead of us and the university people. Next slide. I guess I'll turn it back over to Mike and Aaron.
All right, thanks, Paul. Can everybody hear me okay?
Yep.
Okay. All right. So next slide, please. We're going to take a brief look at some of the surface sampling results now. So this plot shows a rundown in terms of percentage of the background sample results for the grab samples, the micro vacuums, the sponge samples, and then all of the samples combined on the right-hand side here. And each of the bars is shaded by category. So either adjusted detect in dark orange, detect in yellow, indeterminate in light blue, and non-detect in dark blue. So out of the 35 field samples for the background, 12 out of the 35, or about 34% of those samples, had detectable spores, with about 14% being detect and 20% being adjusted detect. 37% of all the samples were indeterminate and 29% were non-detect. From all those samples, there was a total of 11 microvacs, where roughly half of them were either detect or adjusted detect. So, and a majority of the indeterminate samples came from the grab samples. Both the field and media blanks were all non-detect for the background. So all in all, it's rather surprising to see how many hits we got in the background samples. Next slide, please. In terms of average recovery by matrix type, how do we stand based on the detectable levels of spores? Well, for asphalt, and asphalt had the highest recovery of overall of around 10 to the 5th CFU per square foot, which were mainly from the sponge stick sample types. Gravel and ground litter had the next highest recoveries of around 10 to the 2 CFUs per square meter. These recoveries are average values from all the samples of that matrix type. One possibility that could explain the presence of spores prior to inoculation may be due to transport from an adjacent field study, which was used for similar EPA research in 2016. It's been shown from previous studies that spores can survive in the soil for many years. Additionally, there's always the potential for background contamination and also the potential naturally occurring spores that are present in the environment. Next slide, please. Regarding the pre-decon sampling results, out of the 200 samples, 69% of them were detect, 24% of them were adjusted detect, and 8% were indeterminate. And just one sample from a microvac sample was a non-detect. Out of the indeterminate samples, most of them came from grab samples of grass and leaf surface matrices. So with about 92% of all the samples having detectable spores in the pre-decon sampling round, this gives us a pretty good sense that the inoculation was successful at contaminating the area. Next slide, please. So in terms of average recovery by matrix type, the highest recoveries in the pre-decon sample phase came from glass, gravel, ground litter, leaves, and metal surfaces, while the wooden decking material had the lowest recovery of all matrix types. Average recoveries range from about 10 to the 4 to to 10 to the 6th CFU per square foot, which is about in range of 10 to the 6th CFU per square foot. That's the same order of magnitude that we obtained from the RMC sample result. Next slide, please. During the pre and post decon sampling, we situated a total of 8 pairs, co-located pairs of samples for sponge sticks and microvacs per each matrix of asphalt and concrete. And this was to understand if there were differences in the recovery based on the sample type for the same area. In general, there were some differences. Sponge sticks recovered about 2 orders of magnitude more spores than the 37 millimeter vacuum cassettes, showing us that sponge sticks may have a better spore recovery than those microvacs, particularly using this type of microvac pump. Next slide, please. We also recorded evidence of spore transport outside of the inoculated areas. So in the figure on the right, you can see that our wide area demonstration test area outlined in light blue. And the red shaded areas within the test areas are those regions that were directly inoculated with spores. Around the perimeter of the test site, you can see points where we situated our dry filter units. And in total, 8 out of 10 of those DFU samplers were detected during the pre-decon day 1. And all samplers were outside, because all of those samplers were outside the test area. The text also occurred on pre-decon day 2, and then again on the post-decon day. Several surface samples were also collected in areas that were not directly inoculated. 15 out of 19 of those samples collected in non-inoculated areas resulted in detectable spores, but were an average of 1 to 3 orders of magnitude lower in recovery than those inoculated areas. Next slide, please. So for the post-decon sample results, 38 out of 199, or about 19% of those samples, had detectable levels of spores. However, only 4 of those were true detects. 45% of the total samples were indeterminate, and 36% of those samples were non-detect. You'll see that the total number of samples is 199 because one of our sponge sticks was lost along the way and did not make its way back to the lab, which is actually a pretty good statistic for recovery of all of our samples out of the 879 samples. And to unpack these results a little bit further, 90% or an overwhelming majority of the grab samples were indeterminate. Most of the detects and adjusted detects came from the micro vacuum samples. Next slide, please. The highest average post-decon recoveries came from the grass samples at about 10 to the 6 CFU per square foot, whereas the other sample matrices had much lower post-decon recoveries of only about 10 to the 1 or 10 to the 2 CFU per square foot. So even though there were detects, the average spore recovery was definitely greatly reduced compared to the pre-decon levels. Next slide, please. All right, so to wrap up some of the results section with some of the lessons learned that we determined along the way of this whole study, we highly recommend conducting a practice run on the sampling tools and procedures to identify any potential issues in advance. This includes pre-calibrating and verifying the operation of all sampling equipment, because, for example, we experienced some flow issues with our micro vacuum sampling pumps, which inevitably got wet from bleach in the decon line. We also learned that pre-packaging of the backpacks was very helpful, but we need to include extra supplies such as gloves, wipes, and garbage bags, just in case something was dropped along the way. We had some trouble with teams not being able to distinguish between kits that were labeled for field blanks and regular samples, so a different colored bag or a larger label could potentially be helpful. The electric shears for cutting grass were not the most ideal for collecting grass samples, as it caused some issues obtaining the sample. Also, the grass was not as tall and grown as we expected it to be. In terms of the electric shears, there were many operational parts, so it was more difficult to also decontaminate and take those pieces out of the hot zone. And finally, many of the sampling teams did not enjoy taking multiple micro vacuum samples per entry. So we have realized that we need to split up those samples into multiple entries when this is done again in the future. Next slide, please. And to conclude the sampling results section, we determined that there were several detects among the background samples, which was a bit surprising, several non-detects among the pre-decon samples, which was also surprising, and several detects among the post-decon samples. Many of the grab samples results were overwhelmingly indeterminate, which was likely due to background organisms being present on our filter plates. So as a result, we have an upcoming lab research project that's planned to help us determine how we can reduce the background contamination and using methods such as heat treatment. And finally, we need to establish better guidelines on how to interpret the non-detects, the indeterminates, and the data below the level of quantitation if they should be considered true hits. So that concludes my section here. And with that, we'll go to the next slide, and I'll hand the presentation over to Dr. Odions.
Great. Thank you, Mike. Are you able to hear me?
Yes, I can hear you.
Great. Thank you so much. So you've heard a lot about the wide area demonstration. And the question is now essentially, what are we going to do with all this knowledge? Next slide, please. So the first thing that we're working on is the development of guidance documents for specifically US Coast Guard as the main stakeholder for this AnCOR effort, but it will also contain a lot of information that, on the wide area remediation that can be used by local, state, tribal, and other federal entities, including EPA. Next slide. We'll also be working on what we call a dashboard of tools to support the biological agent release response decisions. And this effort will consist of development of this dashboard, looking at what tools already exist, how they are working together, how are they potentially not working together, and come up with a standardized framework to guide the further development of all the online tools that we are developing or have developed in the past. We also have set aside efforts to develop additional decision support tools. And on the right side, you see an example of all those tools that have already been developed as part of this AnCOR program or prior to this effort. And last but not least, we also clearly are working on updates for the various tools that have been developed in the past. The link at the bottom of this website is a good reference point to look at the various tools that have been developed by the Homeland Security Research Program. Next slide, please. The other thing that we're looking forward to is having training with our colleagues at the US Coast Guard, more specifically having tabletop exercises in this fiscal year and next fiscal year at the 3 locations in New Jersey, Alabama, and California. And I think that will be an excellent opportunity to train a lot of people and make them aware of the efforts that came out of this wide area demonstration, but as well as the whole AnCOR program. Next slide, please. So last but not least, we also want to make sure that the larger community is aware of these efforts. So we are working, and we have already published journal articles on the various efforts under the AnCOR program, as well as EPA reports that are publicly available on the websites you see at the bottom right, as well as technical summaries. And a lot of this information will also be presented at the EPA Decontamination Conference, which will be held on December 5 through 7, 2023 in Charleston, South Carolina. If you go to the website at the bottom of the screen, you will find a direct link to how to get information about this conference. Next slide. So you have heard so far actually from only 5 or 6 people, and we should recognize that there are many other people that participated in this exercise, and some of them are shown here on the right side. We just did not have the time to introduce everybody to this effort. And this is only still a small subset of everybody who participated in the wide area demonstration. We had a very large group of samplers that came and helped us tremendously in doing the task that they were asked to do. And without their participation, this would not have been possible. Some of them on the next slide will actually show who they are, and the many more includes all those people that I just alluded to. So we thank you for attending this webinar. I know it was a little bit longer than we normally have our webinars, but we are happy to answer any questions that you may have.
We have a question regarding how the decontaminants fare in sub-zero temperatures. They specify the polar vortex temperatures that might be experienced in our northern states, such as the Dakotas and Minnesota, around 20 to 30 degrees, negative 20 to 30 degrees, or even lower.
I think Worth Kelvy might be a good person to answer this.
Yes, I think I had sent information to one of the moderators to put that in the chat, but just for the benefit of everyone, decon in cold sub-zero temperatures is very challenging. We, a few years back, had done some collaboration with the Canadian government looking at including additives in the decon formulation like calcium chloride to suppress the freezing point. We were effective at getting that freezing point suppressed for minus 30, minus 20, minus 10 degrees C, but the efficacy wasn't quite there. So we have a so-so solution, I would say, but there's a lot more work to be done. Hope that answers the question.
We've received a question if there are any instances of the decontaminating agents reacting with chemicals.
I'll try to give that an answer. Yes, there is a possibility that the chemicals that we use can react with chemicals that are already there. A couple of things can happen. Of course, you can have a reaction that is not what you want to have, and you get a something that you're not looking for. The other thing that maybe more not visible is that you create a reaction with a chemical, and that essentially creates a demand on the amount of chemical that you are actually applying to decontaminate the area. If that is happening, and that is maybe not really a chemical, but it might be more a material, then you may need to apply more of a specific decontaminant to overcome that hurdle.
And Lucas, maybe the question was react in a favorable way, such as if there is a chemical contaminant, would these decontaminants work to neutralize? I think you could answer that one better than any of us as well.
Okay, I missed that part. No, that's a very good question as well. So can these chemicals, HDH and peroxyacetic acid, work for chemicals? The answer is yes. We had the Homeland Security Research Program has a lot of information on that. I alluded to the website earlier where you can find information on how these decontaminants can work against chemical warfare agents, potentially fentanyl, or potentially pesticides or other chemicals of concern.
Question about any follow-up webinars in the future. We have a emergency response webinar series. So there's regular webinars, there's a website, and they're posted, the recordings are posted there. So there's ones that have happened in the past that may be of interest to people. I would definitely recommend checking that out.
Is there a report on the rigid boat decon available?
I'll answer that question. If you want to email me, I can send you the report. Our website is being updated, so it's not easily to find. It is available. All of our information we try and make publicly available, not classified.
Are most of these decontaminants sourced from US suppliers, or are many sourced from overseas sources?
Oh, that's a good question. As far as the products from the vendors are US source. So like high test hypochlorite, you can find that in any pool supply store. The jet ag, you can find that at your agricultural pesticide suppliers. Now, where the actual chemicals are being sourced, I don't know. Maybe someone else can comment on that.
They're going to be produced in the US. They're not going to be produced overseas or anywhere.
We've received another question. How fast can a team be deployed for this kind of decontamination?
The goal of the project was to use commercially off-the-shelf available technology and chemicals. So it would all depend on finding a contractor to apply these decontaminants. So that's not an easy question to answer, but there are companies out there that could potentially, that have the knowledge and the expertise and the training to do this.
Yeah, and just to follow on Shannon's from a 30,000 foot level, EPA is the federal asset. You know, if there is an incident, you work through local and state hazmat and environmental agencies. When the job can't be handled at that level, then there is a request for federal. We, as EPA, we're usually not, maybe not the first responder, not the fire hazmat person that immediately responds via 911. And it kind of depends on the scale and the type of incident, but I'm thinking biological incident. There's state and local maybe respond, request federal assets. FBI and CDC do their judiciary, evidentiary sample collection and health surveillance. And then EPA is the consequence management, the mitigation of exposure risk. So we have on-scene coordinators. Those are our boots on the ground emergency responders in every region. They'll be there ready within, a short period of time, hours to a day. But we may not be tasked to doing the job until after it's relinquished to us from law enforcement.
There is a question regarding a larger vessel. Has the potential contamination of a large vessel like a cruise ship been looked into as part of this wide area decontamination research? As with the size of modern cruise ships, that seems challenging.
We did not look at large ships as cruise ships. We looked at larger vessels within the Coast Guard fleet, such as our larger cutters. A lot of these systems have exterior washdown systems that could be used to apply liquid sporicide, such as a hypochlorite. And so as part of the vessel decon demonstration, we looked at applying pH adjusted bleach on the exterior of the vessel, in addition to those 3 different approaches that I mentioned during my presentation. But we did not look at a large ship such as a cruise ship, no.
There is another question regarding the environmental impact of decontamination. Is there concern with high disinfectant levels for the environment?
Okay, so I'll try to take this one. There's always a concern when you're spraying chemicals into the environment, right? We need to be cognizant of that. When we would use these approaches, there would be a higher risk of human health impacts from the contaminants we're trying to attack. For these chlorinating and for the chlorinating agents in the environment, soil and organic load tends to neutralize those relatively quickly, so they turn into salts and water. And then the peroxyacetic acid, similarly, it has a little bit more robustness with regard to organic matter, but they typically break down into non-hazardous, non-dangerous constituents in the environment.
There's another question along the same lines. How would this affect areas such as streams and wetlands, such as those covered under the CWA 404 waters of the US?
Yeah, so similarly, we obviously try and protect waters of the US. EPA's, in charge of protecting waters of the US. And as part of any test we do an assessment of what our impacts as a test would be. Certain activities are exempt when there's an emergency response, when there's a greater threat from, say, a biological or chemical agent. But as EPA, whether you're talking about emergency responders or the researchers, that protecting the environment is always the ultimate objective. So it's always in the back of our mind what we're doing. We're cognizant of how it's going to impact downstream and long-term effects. I hope that answered the question.
So thank you all for those questions, those who did ask. And if you have any follow-up questions or any questions you want to have you can reach out to our researchers. Their information is available. And with that, we can conclude. Thank you all for joining. Thanks to our speakers.